Okay. Welcome, everyone. Good morning in Australian time. Good evening in good
In
evening, Dr.
Austin.
Professor Jorge Zornberg, because it's your evening time. We have webinar number 48, Sustainability Benefits of Adopting Geosynthetics in Roadway Design with Professor Zornberg. I will just say a couple of sentences about IGS and our ACIGS, so Australian chapter of IGS. As you can see from the map, we are pretty well known in geosynthetic world, and we have chapters in most of the developed countries. We would like to encourage you to join our forces at Australasian chapter of IGS. Thanks to the members, we can organize different events. So, for example, in April, we have a webinar with Chris Lawson about geosynthetic reinforced fields used in marine engineering applications. Will have also one webinar in March with Dr. Chu. However, more information will be coming on our website and bulletin. In November, we will have academic masterclass on geosynthetics 2026. It was also known as Educate the Educators. With Professor Tim Stark and Malek Bauza. It will be end of November, and if you would like to sponsor or you can please contact us. Um, and in 2027, I'm pleased to announce that we have GINZ 2027 conference. It will be focused on mining, but also it will cover other geosynthetics areas. It will be August 2027 and more information will be coming. So um, thank you, company members, for supporting us. These are company members for 2026. And I won't read all the bio of Professor Zornberg because I know that his presentation is quite long. So I don't want to waste any time. If you need certificate, please let us know. We can send it to you. And also, if you have any questions, please post in Q&A, and we will do the Q&A session at the end. After you, Professor.
Very good. So welcome everyone. I'm going to be sharing my screen. Let me make sure that everything is working fine. Uh, there you go. So do you see my screen? Can you confirm?
It's slow. Yes, yes, it's
Perfect. And you can hear me well. Is that
yes,
right?
yes.
All right. Well, it's such a pleasure to be here. It's always a delight for me to have the opportunity to share some information with my friends from ACIGS. So this time I'm going to be talking about sustainability, but specifically the benefits of sustainability when it comes to the design of roadways. Let me tell you why we're going to focus on roadways. Okay, so it turns out that many could argue that the roadway network, worldwide roadway network, is the largest public asset in the world. More than any other types of infrastructure when it comes to public infrastructure, this is the largest asset that we have. As a reference, we have 873,000 kilometers of roadways in Australia. It's hard to put our head on what really is that we mean with almost 900,000 kilometers. So as a reference, the circumference of the Earth around the equator is only 40,000 kilometers. So if we were to get all the roads in Australia and get them around the equator, we would go once and twice and 3 times and 5 times and 20 times, 22 times around the equator just with the roadways in Australia. It's a lot. It's a lot. And we need to build them. We need to maintain them. We need to operate them. As a reference as well, the US network, roadway network, is over 6 million, almost 7 million kilometers. So we would need to go 170 times around the equator with US roads. If we go to the world, and I want you to remember this number, 64 million kilometers, 64 million kilometers. We need to go 1,600 times with our roads around the equator just to have a sense of what is that we mean by the roadway network. A different way of looking at these world roadways here is a network in total length. So ordered by total length, and here is Australia, number 9. So certainly you're not ninth in terms of population. You're very big, but not ninth in terms of population. But again, we are talking about a very, very substantial network of roadways. Now, when we design roadways, a good design of roadways, unlike many other systems, we design roadways so that they fail. If we design a roadway that doesn't fail, is a poor design, because a good design of a roadway is one in which we target a design, let's say, so that the design life is 15 years or 20 years, and is a design life based on serviceability. So it's not trivial to design roadways. We're not going to get too much into design, but I want to tell you how geosynthetics will help designers to obtain a better performance on our roadways. Just as a reference, the typical geosynthetics that we would use in roadways are going to be geotextiles, woven, non-woven geotextiles, or geogrids, uniaxial, biaxial, multi-axial, different polymers, geocells. Now, when it comes in this presentation, roadways is a lot of things. It's embankments, it's bridges. But in this particular presentation, I am only gonna focus on the structural package of a roadway. Something like this. So going from the top down, I'm gonna specifically focus on flexible pavements. That is, pavements in which we do have an asphaltic layer as road at the very surface. So where do geosynthetics go in this structural package in the roadway? And this is a complicated thing, because we can use geosynthetics in way too many forms and different types and different functions and different applications. So a little bit of what I'm going to try to do for you here is to tell you where do we use them. And specifically, I'm going to cover 6 different applications. And essentially, when it comes to the structural package, we can use geosynthetics. So for some form of mechanical functions, let's call in separation if we want to keep dissimilar materials separate, or we can call it reinforcement if we want to develop tensile forces to provide stability, or I'm going to call it stiffening. It is a cousin of reinforcement, but in this case, our goal is to develop tensile forces to improve the modulus. When we design a roadway, the modulus, the stiffness of the system, is particularly relevant at low displacements. But we also can have hydraulic functions, in this case, filter, or as a barrier, or as in-plane drainage. Okay, so we have all these many functions in which we can make good use of geosynthetics, specifically in roadways. So what I'm going to be talking about, I'm going to step back, and I'm a professor. I'm a professor at the University of Texas at Austin. So when I teach students about design, about infrastructure, typically we focus too much and almost exclusively in performance. How to design so that our system, our roadway in this case, achieves a certain behavior. And there's, of course, that's the part of engineering that we need to teach. The one aspect that happens is that when my students go out to the real world, and they say, okay, now I'm going to design for performance. So everyone is going to choose the roadway or the wall or the cover system or the barrier system that performs the best. And that's not how the world works. Essentially, the way that it works is that for a given performance that is required for certain design criteria, very often, the choice is going to be to select what is the alternative. We typically have, as designers, we have more than one alternative to design the same thing. Out of the different alternatives, where very often my students end up choosing the one with the lowest cost. And very soon we need to become experts on cost, even though I don't teach you about that at the university. Well, in this case, I would say I'm gonna contend that there is another very important aspect that we need to take into consideration when it comes to the selection of alternatives. Again, we have a design to put together, and multiple alternatives can satisfy a given performance. And the idea is that each alternative may behave differently. Each alternative may have a different cost, and I'm going to talk about a third important factor, not performance, not cost, but sustainability. And the idea is then when we are going to get into evaluating alternatives in the US, and I suspect that that's also the case in Australia, the most common approach from the construction management point of view is the design, bid, build. And that is very prone to choose the lowest cost alternative. However, it has been known, and it is well known, that really what we want for a given alternative is not necessarily to choose the lowest cost, even though cost is very important, but we want to choose the alternative that has the highest value. And the reason that I'm telling you this is because I think that when we start talking about the best value of our engineering solution, is a particularly good framework in which we can start taking into consideration sustainability. So essentially, this is all the actual framework is called value engineering. And the idea is that out of the different alternatives, we're going to be able to increase the value of our alternative, not strictly by decreasing the cost. We can increase the value by improving the performance, or by decreasing the cost, or I'm going to toss at you another factor, or by increasing the sustainability of our solution. This is very important, and in worldwide, we're starting to learn how to handle this additional important factor. There are many different ways in which we can quantify sustainability or the problems that worldwide we're facing regarding weather. Weather and global warming. And there are many different ways in which we can quantify how we're doing. Let me tell you one that I like seeing. This is a way in which we can quantify, for example, if we have a problem about global warming, or if we have a problem and we should care about sustainability. This is one that I'm going to contend with you that is a relevant one. In the US, the NOAA, there is a National Center for Environmental Information, and a very specific set of data that they keep track of is what is called the US $1 billion weather disasters. Billion with a B, $1 billion. So essentially, this is a series of measurements that this agency will take care of and will quantify and will put in evidence if the cost of a weather disaster, maybe a drought, maybe a flooding, maybe a hurricane, exceeds in damages $1 billion. And what this graph shows in here is in the vertical axis, the number of events per year that exceed in cost, weather events that exceed $1 billion. And here in the horizontal axis, January, February per month. And the cumulative values are indicated here. So, and this has been started in the 1980s. So all these gray lines that you see in here are essentially the cumulative cost of billion-dollar disasters or number of billion-dollar disasters in the US over the years. And let's see if we're having a problem with the most recent years. So here in color, what we show in color, there are many different lines, but the ones in colors are the six largest, the 6 years in which we had the largest number of billion-dollar disasters. And let's see 2024. Here's 2024. It's almost the one in which we have the largest number of disasters, $27 billion disasters. But we also have 2024 and we also have 2023 is the one that we have with the highest number of billion-dollar disasters. But we also have, look at this, 2022. And also we have 2021, and we also have 2020. So essentially out of the 6 years with the highest number of billion-dollar disasters, the last 5 years are among those 6. So we are getting worse. We are getting worse. And there are many different indicators. This is just one of them. Probably the most well-known indicator is the carbon footprint. So here we have, there are many different ways in which we can quantify the environmental impact. One of them is greenhouse gas emissions, and one of these emissions is the carbon footprint, and it has become probably a standard. And here we have, for different countries or different regions of the world, how the carbon footprint has been growing on a yearly basis. And we can see that, I don't know, in the last century, in the 1900 up to 1900s, the emissions were comparatively small. Blue is US, these different shades of brown is Europe. We were essentially, the US and Europe carried all the footprint of carbon emissions. It is essentially, maybe even the 1950s, less than 100 years ago, still the US and Europe were the biggest the ones that with the biggest emissions in CO2, equivalent CO2. It is only around the 1980s that things start to change. And here's when we start seeing red means is China, and green is Asia, particularly India. And here we get into 2024, in which we can see the blue and the two browns that are Europe and the US. Now, this accounts for about a third of the carbon emissions. Whereas Australia, here is not Australia, but here is a different way of looking at this. In the previous one is actual total emissions of CO2. This is in percentage at any given year. Again, 1900s, US, Europe, the main contributors. And here in 2024 is more varied. The US and Europe, a third. This is China, probably as much as US and Europe combined. This is Asia, particularly India. And this is Oceania. That includes Australia. So I read this for 2024. I didn't have the 2025 numbers, are not published yet. This is around 1.1, 1.2% of the global world emissions. This is a different way of looking at this. This is the CO2 emissions in Australia per year. And I think this is pandemic 2020, you can see a significant drop. I'm not sure if you became much more conscious about CO2 emissions, but around the 2000s, things started to plateau, and we could argue that even the more recently are even decreasing. You guys are decreasing the total emissions. But this is very significant. Remember that Australia has a big mass area, but a comparatively small population. So this is a different way of looking at it. This is the CO2 emissions per person. So Australia is, here it is, this blue one, peaked in the early 2000s and started to decrease. And to my surprise, the emissions per person in Australia are very, very similar. Look at this, very similar to the ones that we have here in the US and very similar to the ones per person that we have in Canada. So, all right. So this is just to show you that we do have a problem. The emissions, and again, this is only one of the different measures, keep only increasing, and something needs to be done about it. How do we quantify this in our engineering projects? And this is what we care. And this is what we call life cycle assessment. Essentially, we can calculate for a given project what is the cumulative CO2 emissions that correspond to a given project. For example, many of you are in the geosynthetics business, so the embodied carbon footprint of polyethylene granules is smaller than the embodied carbon in polyethylene sheets, and is in turn the lower than the polyethylene the CO2 embodied CO2 in a geogrid. So as we keep processing the system, we keep adding to the embodied CO2. And this is a very well-known cycle. And the idea is that when we want to compare alternatives, we need to quantify what is called an audit, a CO2 audit. So we're going to quantify in our project, a roadway project, a landfill project, an embankment project, what is the cumulative CO2 that will take to, for example, to build an embankment or to build a road. And we can compare the embodied CO2 of different alternatives, and that's how we can make informed decisions about which one of the alternatives not only has the highest performance or the lowest cost, but also is more sustainable. This life cycle assessment could be in different ways. We always need to be very precise on from when to when, and that's what we call it from cradle to gate, is when we're going to evaluate the carbon emissions, embodied carbon of products until we receive them at the project site. The manufacturing of and transportation of materials. Then we have another way to compare is from cradle to build. What is, for different alternatives, what is embodied carbon by the time that we finish the construction, in this case, of my road? That's more accurate than cradle to gate, if we're going to use this as a comparison. The ideal one, but it's hard to quantify, is what is the embodied carbon emissions for not to gate, not to at the time that we build it, but at the end of the design life. And if we compare that, we do the most rigorous and more important comparison that we not always can do cradle to gate. In this presentation, I'm going to walk you through examples. Some of them are going to be cradle to build. Some of them are going to be cradle to grave. All right, so essentially with the carbon audit for a given life cycle, we are going to calculate what are the different contributors of carbon. So that is background on what sustainability and the type of exercise that we're going to go through. But in this particular presentation, I'm going to walk you through 6 different projects, all of them on roadways, all of them with a different application in roadways. Specifically, And I will need to go quickly, but I'm going to walk you through example number one. And what is important about these 6 examples? All of them are real. All of them where the designer came up with at least 2 alternatives, one with geosynthetics, the other without geosynthetics. All these are comparatively old examples. They have already been built. So the decision-making process was performance or most likely cost. No one paid attention to sustainability, even though from now on we can take sustainability into consideration when we're going to be choosing the alternative. But the 6 alternatives that I'm going to tell you, essentially the main criterion to choose among the alternatives, all of them satisfying given performance criteria, was cost. Nonetheless, we're going to do a carbon audit for each one of these 6. And for each one of these 6 projects, we're going to have 2 alternatives with and without geosynthetics. And we're going to see what the audit tells us. What are those 6 projects? 1, 6 different applications. 1, mitigation of reflective cracking in structural asphalt overlays. I'm going to walk you through what I'm telling you about. So if you're not familiar with roadway design, I'm going to come back a little bit into each one of these. Then, second, stabilization of unbound aggregate layers. Third, reduction of layer intermixing. Fourth, reduction of moisture. Very important in roadways, even though typically we don't design as much as we should for that. 5, stabilization of soft subgrades. 6, mitigation of distress due to expansive clays. Big problem in Australia and in Texas, which is where I live. So for each application, this is what I just told you. For each one of these 6 applications, case histories were identified. These case histories have at least 2 alternatives without geosynthetics. We're going to go through the exercise of doing the carbon audit of each one of these alternatives and see what we can find out. So the sustainability is going to be based on the carbon audit. And the way that we're going to calculate these is going to be in tons of CO2 per lane per kilometer. That's how we're going to quantify it. Just as a reference, 1 ton of CO2 is the carbon dioxide that is going to be sequestered by 1.5 hectares in a year. That's what it means, 1 ton. It's a lot. Give me 1.5 hectares of forest. The carbon that is sequestered in that forest is 1 ton of CO2. This exercise, it was not just myself, the one that did it. I did it with very, very smart collaborators, and I want to recognize them. Dr. Subramanian, Dr. Rudy, almost Dr. Yalcin, and Dr. Kumar. And there is a recent paper that was published with a lot more information about the 6 case histories that I'm going to walk you through. All right. So let me walk you through case history number 1. The application in this case is mitigation of asphalt reflective cracking. When do we use geosynthetics to mitigate reflective cracking? It turns out that a very problematic phenomenon that we have when we do an asphalt overlay, when we replace the superficial layer of asphalt, is what is called reflective cracking. And what geosynthetics will help us with is delaying or eliminating this reflective cracking. Let me get back to this. So this is the problem that we have. We are retrofitting a roadway. So very often what we do is we mill, let's say 5 centimeters of the top asphalt layer, and we're going to replace it. And we're happy because all our pre-existing cracks are now covered with a new easy to ride surface. But there is a problem. This surface, the pre-existing cracks ask a lot from the newly placed asphalt overlay, and we have a stress concentration at the tip of our crack, pre-existing crack, and this is going to be reflected. And we're not very happy. We're not very happy because the brand new asphalt overlay, maybe in a year, maybe less, maybe a little bit more, may reflect the pre-existing cracks. So how can geosynthetic help us? There are at least 2 ways in which geosynthetics can help us. One way that I'm showing here is what is called tension development mechanism. Essentially, what is going to happen is that these highly concentrated stresses that develop at the tip of our pre-existing crack are going to be distributed over a wider area. And what this is going to do is, even though the solicitations are still there, they are distributed, so this will not trigger a crack. A highly concentrated energy is what triggers the crack. There is a different way. That is stress relief. I'm not going to get into the details, but just to tell you that there is more than one way in which geosynthetics can help. But if we go for use of geosynthetics to distribute the tensions, then the functions is what we need now. The function is going to be reinforcement, and perhaps we're also going to have separation. I didn't tell you about stress relief, but this would be the situation, the mechanism or the function that we would need. It could be, in some cases, these geosynthetics come also with an additional function of barrier. And very common one would be when we have the barrier and the reinforcement at the same time. So I gave you a very brief overview. I could spend a long time in telling you how this works and how to design for it and how to select the geosynthetics. I'm not going to do that. Instead, I'm going to walk you through a case history. This case history is in Texas, close nearby Austin. This is in Bastrop, near Austin in Texas. And in this particular project, essentially the pre-existing roadway was in distress. And the asphaltic layer was 150 millimeters or so. And the idea was to replace a part to mill the surface of this asphaltic layer and to replace it. One way in which this can be done is by replacing it with a fair amount of asphalt. A different way is to decrease the thickness of the asphaltic layer, but instead to add a geosynthetic that is going to have the function, mainly a reinforcement function. So let me show you the two alternatives. And again, we didn't do these alternatives. These were the alternatives that the designers considered at the time of selecting the final solution. So the objective was to mitigate reflective cracking. And potentially, now we're learning that there is also an increased structural capacity, but the primary objective was to mitigate reflective cracking. So this is the conventional design. The original asphalt layer will remain in place, and it would be replaced with 5 inches of new asphalt overlay. Asphalt carries, just so you know, a significant carbon footprint. So if we can decrease the mass of asphalt, we're going to be decreasing the carbon footprint. So this is the alternative. Instead of having 5 inches or 125 millimeters of asphalt, what about if we have 3 inches, 75 or so millimeters of asphalt with a geogrid? I'm not going to walk you through the details of this particular project, but essentially what the exercise involves from the moment that each one of the different materials of these two alternatives is created, is transported, and is constructed, we're going to do a carbon audit for the as-built solution. So this is the construction. It involved milling, it involved placing a binder tag coat, it involved placing the geosynthetic, it involved constructing the HMA, the hot mix asphaltic overlay. So these are the two alternatives. Again, conventional without geosynthetics. With geosynthetics, yes, we do have an extra geosynthetic that we need to account for, but this came in lieu of 2 inches of asphalt, 50 millimeters of asphalt. So if we can do the carbon audit, and here what I'm going to show you is a carbon audit as quantified in tons of embodied carbon per lane kilometer. So per lane, per kilometer, in this particular case, there are 4 lanes, but per lane, one of the 4 lanes per kilometer. The project was quite long, but in one lane, in 1 kilometer, this is a quantification of the carbon audit. Without geosynthetics, we have a component, and most important component, blue, is material and transportation and construction. Here is almost 70 tons per car per lane kilometer. And when we calculate the embodied carbon of the geosynthetic solution, we are on the order of 45. This is a different way of looking at it. In this case, per material only, 100% in the conventional solution is the embodied carbon for the creation of the asphaltic layer, transportation of the asphaltic layer, and placement of the asphaltic layer. When we go to the geosynthetic solution, we have comparison. If this is 100%, then we have less asphalt, a geosynthetic layer, a geogreen in this particular case, and a significantly smaller, 32% smaller. And I want you to look not only at the percentage, because the percentage of the total carbon may be a little bit deceiving. I want you to think of 22 tons of embodied carbon per lane kilometer. This is what this geosynthetic solution could save if, instead of going for the conventional solution, we go for the geosynthetic solution. Let me take you to case history number 2. In this case, it's going to be a different objective. The objective will be to increase the modulus of the base layer. When we design a roadway, our base, our aggregate layer, what we do ask from this aggregate layer is to increase the modulus. It needs to have a good modulus. It needs to be stiff. What the geosynthetics will do, if we stabilize it with geosynthetics, is to increase that modulus. This has implication, for example, in decreasing the thickness of the unbound aggregate layer that is required for a given design life. A different way of looking at this is that for a given aggregate thickness, it will increase the design life. How does it work? There's an entire discussion on how that would the geosynthetic improve the performance of the unbound aggregate. At this point, I'm going to tell you there was a lot of discussion about these different mechanisms that were proposed. There is consensus now. The consensus is that the mechanism is called lateral restraint. Let me tell you what lateral restraint means. So here we have a simple layer, non-stabilized road base with a base layer with a cyclic load, which is the roadway, the wheels, the wheel load. There is a tendency over time to have permanent deflections in the unbound aggregate, in the gravel, essentially. Those deflections may be particularly detrimental to performance. Why? Remember, gravel is an excellent material from the stability point of view, from the bearing capacity point of view, is excellent, but if and only if this gravel is confined. And when we construct the road, we compact this aggregate. So as compacted, as soon as it's constructed, we have a highly compacted, very dense and confined aggregate layer. But this mechanism of trying to displace laterally the particles of our unbound aggregate, and I'm going to exaggerate in this cartoon, but may lead to something like this. Particles start moving laterally, and this creates a very detrimental domino effect. The particle moves laterally, and we're talking about very little movements, fractions of a millimeter. But if the particle moves, we lose confinement. And if the aggregate loses confinement, we lose modulus. And if we lose modulus in a roadway, essentially a nicely distributed load that reaches the subgrade in a well-distributed area now gets concentrated. And for example, if our design criterion is based on rutting depth, deformation at the wheel path, then we have a problem. The alternative is that the geosynthetic that we place in here will minimize or prevent this lateral movement. And by doing so, we're going to maintain, some could argue that it's even increase the modulus of our unbound aggregate layer. Okay, so only now that we understood, and it's not trivial how we come up with this mechanism. Only now that we understood the mechanism is that we can tap into what is the geos. We need the mechanisms. Then we need the property, the functions. And only once we know the functions is that we're going to go to the properties. What is the function that in this particular case we need? The function is called stiffening. And the idea is that the selection of this geosynthetic is to maintain the confinement, is to lead to an increased modulus in relation to the one that we would have if this geosynthetic were not in place. Let me take you to a project. The project is in Ohio, near the Great Lakes, and is a reconstruction of Interstate Highway 90. In this particular case, in this particular project, the project involved a very challenging effect. This is right next to Lake Erie. And in the Great Lakes, there is a problem that is called the lakes effect snow. So essentially, when we have very low temperatures and the wind comes on top of Lake Erie, then it collects moisture because the lake is comparatively warmer. It collects moisture, but as soon as the wind, now carrying moisture, reaches shore again, it's cold again, and essentially we create a snow effect just by the moisture that is in the air. The reason that I'm explaining this is because a very important condition in this particular project was it need to be constructed quickly. So let me show you the two alternatives. Alternative number one, and all this was constructed below grade. So here, when I'm talking about these different layers of of aggregate, essentially this was from the existing surface grade down. It required an excavation to place, in this case, Ashton number 2 stone, Ohio DOT number 304 aggregate. These are different types of aggregate materials. And finally, the asphaltic layer. If we benefit from the stiffening, from the stabilization of these unbound aggregates, the designers came up with an equivalent, from the performance point of view, an equivalent system. And this is the equivalent system. Let's excavate less. Let's still keep 2 layers of aggregate, but thinner layers of aggregate. So these are the two alternatives. One, more excavation, more aggregate. The other, less excavation, less aggregate, plus a geogrid. We evaluate performance. The designers did that. We evaluate cost. I'm pretty sure that this was selected because it was more cost effective. But what we're going to do now, after the fact, is to evaluate the carbon footprint. All right, so this just very quickly, this is the construction of a stabilized unbound aggregate layer. Here's the placement of the geogrid in this particular case, the unbound aggregate. It was reduced the thickness. Here's a view of the geosynthetic with the unbound aggregate, and here's a compaction. The very important step in the construction is the compaction. Here's a view. It's a nice picture because here we have the excavation. We have at the top of the excavation, we have the geogrid layer. Then we have the 2 aggregates in this particular case, and finally the asphaltic surface. Okay, so this is the exercise for today. Well, there's a lot that we can talk about the design and the mechanisms and the selection process, but in this case, the focus is on doing an audit of these 2 alternatives, a sustainability audit, a carbon footprint audit, conventional design, alternative design with geosynthetics. These are the results. Again, in this bar, we have the total carbon footprint as quantified by the materials, by its transportation, orange, and by its construction. At the time, we didn't care, or we didn't pay attention to the significant carbon footprint that is carried by the asphaltic layer, which the unbound aggregates do not have such a significant. My opinion, if we were to do this today, probably we would try to achieve the same performance, but with a thinner asphaltic layer, because that will have a significant component in the carbon footprint. This is the same audit, but shown in a different way as a pie chart, but in this case per material, asphaltic layer, aggregate layers, and this is the cost of the undercut, and this is the geosynthetic layer. Is a 11% decrease in relation to the conventional aggregate, but look at the magnitude of the tons of CO2 per lane kilometer. It's even higher than the previous example, even though as a percentage is smaller. Over 30 tons of carbon footprint of CO2 equivalent is a lot. Let me walk you through our third example, and I'm going to pay attention to my timeline. Okay, so third example. Maybe I'm going to rush through some of the examples. This is layer intermixing. So in this particular case, we want to avoid contamination of unbound aggregate layers with fine grained subgrade. This is what we're talking about. We have a subgrade that is essentially a clay subgrade, and we put it in contact with our very expensive and very good base layer. What we do not pay attention in design, but it happens, is that over time, we will have a intermixing of those two materials. Either there are two mechanisms, either because we lose some of the aggregate particles, some of the gravel particles into the subgrade, there's some sort of localized bearing capacity problem, or maybe because we pump up. If there is water, and we will pump up the fines into the base layer. Either way, for all practical purposes, this base, and we design this base for a given thickness, we lose that base over time. This solution is very, very simple, very simple. Let's get a comparatively inexpensive geosynthetic, sometimes just a non-woven geotextile, maybe a woven geotextile, and let's keep the aggregate and the subgrade separate. And in doing so, we're going to maintain the integrity of the base layer that we want so much to perform because of its stiffness. So only now that we have this mechanisms is that we can come up with what are the functions. The function is going to be separation, typically between the subgrade and the subbase, if we do not have a subbase with the base. But very often we're going to have water, so the hydraulic functions such as filtration is going to be particularly relevant. I'm going to walk you through a case history. The advantage of this case history, and I'm not going to have that much time to show you, is that unlike the previous two examples in which I walk you through an audit from cradle to as built, and here I'm going to take you from cradle, passing the as built into the grave. So I'm going to do the carbon audit up to the end of the design life of the roadway. It's not every structure that we can do this. In this particular case, this was a monitored structure, so we have the data to do this analysis. So it was an experimental section, so that's why we have so much data. But the challenge is to quantify. And this is a very big challenge. We know that geotextiles work well as separators, but collecting the data is tedious and time-consuming and difficult to get. This is the two solutions. Again, we're going to compare this at the end of the design life, not as constructed. So what ended up happening is that the conventional design without geosynthetic, to get to the end of the design life of the next solution that I'm going to show you, is this one. Same thickness of the asphaltic layer, same thickness of the base layer, plus a geotextile. So where's the savings? Well, the savings is that by the end of the design life of the alternative that we designed with a geosynthetic, we reached the design life. The design life in this particular case was reaching a rutting depth, a vertical displacements of 20 millimeters. That's end of the design life. To reach the end of the design life in the alternative with geosynthetic, we had to reach the same end of the design, the same period of time, but after having retrofitted the asphaltic layer in the conventional design. So in order to reach the same time, the section that was the conventional design had to go, remember the milling and asphalt overlay? This section had to go through that process twice. So this top 35 millimeters had to be milled and replaced twice by the time that this other alternative only had to be done this once. Twice that we have 35 millimeters, transportation, materials, and placement costs, and embodied carbon. This is then the information. This is the hard to get data. This is rutting depth versus load, number of cycles. Number of cycles is an equivalent of time. So we reach the design criterion was 20 millimeters, a design life that, after which we reach a rutting depth of 20 millimeters. This is a measure of number of cycles of a standard wheel load, 55,000 for the control section without geosynthetics, 103,000 easels cycles of a standard load for the section with geosynthetic. Significantly longer design life, and consequently, the control section had to go through not a reconstruction, but a retrofitting twice to reach, give or take, 100,000 easels. So here we have the two alternatives again. Conventional design, again, same thicknesses, but in this case with asphalt overlay reconstruction. And these are the comparisons. If we look at this comparison again, we have the base, the asphalt, the contribution from the asphaltic layer, the base, and the subgrade. And here is with geosynthetic, we have in this pie chart, a contribution, a savings of 38% of the carbon footprint using as a reference the conventional design. Or this is huge, 44 tons of equivalent carbon per lane per kilometer. I don't wanna take more time than what you planned for. So for me is 6:50. So I'm gonna do the following. I walk you through 3 case histories. I have 3 more. I'm not gonna show them to you. I'm just gonna tell you the final results, and I will owe you the information about these 3 because I wanna get to the end. So this next case history is a case history in which the issue was to mitigate the drainage, the benefit of having an in-plane drainage, enhanced drainage with a new type of geosynthetic that is called the wicking geotextile. And in this particular case, this was done in lieu of using a very special granular material that could serve as a drainage aggregate. I'm not going to show you this, but this is case history number 4. Case history number 5 could be about what about if we have a problem with our subgrade? In this particular case, it's a different problem. It's a problem in which we will use a reinforcement, a geotextile or a geogrid, but the objective is to increase the bearing capacity of my soft subgrade. I owe you how to do it. And I'm gonna just walk you through, this is a very, very interesting case history. This is the case history of involving the construction of the new international airport in Mexico City. Is only one fraction of that humongous project, one that involved a working area, and I'm gonna owe you the case history. It is in the paper that I mentioned, but in this particular case, the solution was using a geogrid and a geotextile separator at the interface between the subgrade and the base. Large quantities of geosynthetics. This was case history number 4. Case history number 5. I gave you another webinar only on this topic that was mitigation of problems associated with expansive clays. And when we have expansive clays in Texas or in Australia, and you have a lot of them, the problem are these longitudinal cracks. The problem are these longitudinal cracks. So if you're driving by Sydney or by Melbourne or by Brisbane, you all have expensive clays. So if you see this type of distress, longitudinal cracks, don't blame the traffic. The problem is the subgrade. And the problem with the subgrade is that the subgrade will swell during the wet season and will shrink during the dry season. We can use different types of geosynthetics. The one that we use a lot in Texas is the use of geogrids to mitigate the distress, that is the development of these longitudinal cracks when we have expansive clays. The case that I'm not gonna show you, but I was planning to show you was case history number 6. This is also very interesting because in this particular case, we have data to walk you through the audit at the end of the design life. So in this particular case, the design criterion for the sections with and without the geosynthetic was a longitudinal crack index of 15%. What is that? Is if you develop a longitudinal crack that is 15% of the length of your section. So how long does it take? And in the case of the control section without geogrids, in this case, it could take about 8-9 years, and in the case with geosynthetics will take over 15 years. And in this particular case, the control section had to go through retrofitting with an overlay. So when we do the comparison, we end up with a comparison of at the end of the design life, which is cradle to grave. All right, so I talked to you about what does it mean to do a carbon audit. I talked to you about 3 of the applications with 3 case histories, and 3 case histories in which we have done the audit. I skipped, but I told you and I promise you that they exist. If you want to go to the reference, is there the audit of 3 additional case histories. So this is a summary. So in case history number 1, this objective was to mitigate reflective cracking, and we saved 22 tons of equivalent carbon per lane kilometer. In case history number 2, the objective was to rigidize the base, and we saved 30 tons of CO2 equivalent per lane kilometer. In case history number 3, we reduced the mixing by placing a geotextile, and we increased the design life of my roadways just by separating the subgrade clay from the base, and we saved 44 tons of equivalent carbon footprint per lane kilometer. These are the 3 case histories that I didn't show you. Reduction of moisture, we saved 18 tons per lane kilometer. Stabilization of soft subgrade, we saved 21 tons, and mitigation of distress due to the presence of expansive clays, 22 tons of carbon footprint. A lot of savings in carbon footprint, but I want to give you a sense of what is that this means. What is that this means? So I'm going to walk you through a hypothetical on what does it mean to save these many tons of equivalent carbon footprint per lane kilometer. Let's do a footprint. So let's consider the following. Let's consider that these 6 case histories that I showed you are representative. These are 6 different applications, very different applications of geosynthetics in roadways. But let's say that they are representative of the cases of the carbon audits that we would do in other cases. That's definitely not true. But let's assume that they are representative. So this means that we could argue that as an average of these 6 case histories weighted by length, we have an average reduction of 26 or so tons of carbon footprint equivalent per lane kilometer. This is for the design life after I constructed it. Let's take a typical design life of 15 years for my roadways. So if we amortize amortize these 26 tons divided by 15 years, we get, instead of the as built, we get on the order of 175 tons of equivalent carbon per lane kilometer per year. Let's do a very, very hypothetical scenario in which, remember that I showed you the world road, the network, the road network worldwide. Remember that it was 64 million kilometers. Let's make the very significant assumption that in the future, these 64 million kilometers will use geosynthetics one way or the other, that geosynthetics become very similar to what we have a base, we have a subgrade, we compact the base, we put asphalt, we put a geosynthetic. They become common use in what roadways? In all of them, using one out of the 6 applications that we have. So what this would mean for these savings of carbon per year, if we use geosynthetics, and for these big assumptions that we make, that the examples that we did are representative, that all the roadways start using geosynthetics, we are saving per year in the world an average reduction of 225 million tons of carbon equivalent per year. What this means, this is equivalent to the carbon footprint that is sequestered by approximately a forest of 100 million hectares in a year. What is 100 million hectares? I did a little bit of geography. I went to your state, the driest of your states. I learned that is South Australia, and Adelaide is. So essentially, if we were using geosynthetics as part of a routine design in roadways, we would be saving on the order of 1.41 times of a forest that has the size of South Australia. Big savings if we end up implementing this as an alternative. And as I mentioned, among the different assets, infrastructure assets that we have, if we make a difference in roadway design, we have the opportunity to make a significant impact because of the sheer volume of roads that we have worldwide. Conclusions. So the frameworks now exists to evaluate in a roadway in this particular case, but in infrastructure in general, not only performance and cost, but also sustainability. This has been geosynthetics has been demonstrated to improve and often significantly the performance. We have focused a lot on how to improve the performance using geosynthetics. But also, we also know that when using geosynthetics in roadways, very often, more often than not, actually almost always, the solution with geosynthetics is also cost effective. But it's not only with increased performance, it's not only cost effective, but I hope that I convinced you that we're well on our way to demonstrate that the solution with geosynthetic consistently provides a lower carbon footprint. So, and even though my example was very hypothetical, the message is that there are very significant opportunities to not only use geosynthetics to improve the performance of our roads, to improve the cost of maintaining and constructing our roads, but also the opportunities to reduce the carbon footprint when using geosynthetics in roadways are simply massive. And with that, I thank you so much for your attention.
Thank you, Professor. That was very informative, especially the sustainability information. It's past the time. However, I think we might have time for one question. That was Phil Pearson. Hello, Jorge. Agree that the use of geosynthetics will provide an opportunity to reduce pavement layer thickness materials. This will provide an immediate sustainability benefit. However, has the long-term performance of these alternative pavement designs been considered? For example, will the geosynthetic pavement perform equivalent or better than the conventional pavement? There is a long established history for the expected performance of a conventional pavement design. So, can the designers be assured of the performance of the geosynthetic alternative pavement? Would an alternative approach be to include geosynthetics in conventional pavement design and measure the sustainability benefits, improved long-term benefit? If so, this is often difficult to measure. Cheers and good to see you again. Phil Pearson.
Yes, the answer is yes. Definitely, we do have the data. It's data that is not trivial to obtain, but just so you know, for example, and I talked about many different ways of using geosynthetics in roadways. I'm assuming that, for example, one of them is to use a geosynthetic to stabilize the ambient aggregate layer. So there is data that shows us, and that's how we design. We're going to design two alternatives that are going to be equivalent, equivalent in terms of performance. And to achieve the alternative of having the same performance, so that means that we're going to reach the end of the design life at the same time. It turns out one way of looking at this is that if you have the geosynthetic, for example, a geogrid in your base aggregate, in your base material, you can decrease the thickness of your ambient aggregate. That's one way of looking at it. But if you're a designer of roadways, we know that an alternative way, but also to solve for the same problem, is let's keep the thickness the same. And maybe that will give you a more conservative way or less risky way. Let's keep the thickness. Let's just add the geogrid. What you're going to see is that the design life, the performance at which you reach the design life is going to be extended, which is essentially a different way of looking at the same problem. But either we, for a given thickness of the base, we get extended design life, or for a given design life, we reduce the thickness. In both cases, we are having benefits. In both cases, we will be improving the sustainability aspect of the problem. There is a lot of literature, and I'll be happy to provide the literature. So the answer is yes, we can stand by the performance of the geosynthetic, provided that we design them correctly.
Thank you. And the last one is also just actually request. Abdallah Adam asked to share the record and materials with them. So the record will be available on our website, probably within a week, and the materials, so probably you can see from the video, but I'm not sure if Professor will share the presentation.
There is a paper, and you're all, maybe I will show you. This presentation is very, very much based on the information in that paper that is recently published.
No worries. Thank you so much for that. And I wish you have a good evening and good night.
Very good.
And
Thank you, everyone. Thank you for the participation.
thank you,
Bye-bye.
everyone. Bye.